Okay. So in this question, we're asked to let W be the set of two by two symmetric matrices, real two by two symmetric matrices, and show that W is a subspace. So here I've got two things. I've got real two by two matrices, which means my field is R, and it's two by two matrices. But there's this symmetric. And what we have to do is we have to know that this means that W equals the set of A, B, C, D in M 2 by 2 R such that B equals C. And that's what we're given. And we want to create a finite set S such that W equals the span of S. And to do this, what we do is we consider X in W. Then X equals A, B, C, D such that B equals C. We can update X using this equality. X equals A, B, B, D, which equals A0, 0, 0 plus 0, B, B0 plus 0, 0, 0, D. And what we're doing is now that we've ensured that this equality is always satisfied, we're splitting up based on our scalars. So A10, 0, 0 plus B01, 10 plus D00, 01. And let S, and what we're going to let S equal the set of these matrices 10, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1. Now that we have S, we need to show that W equals the span of S. So if we let W equal the span of S, this here tells us as X was in W was a generic element of W and X equals A10, 0, 0 plus B01, 10 plus D00, 0, 0, 0, 1. Then X is in the span S. So we've shown that if we're in W, then we're in S. Now, to let, or thus, W is a subset of the span S. Now we want to show the other subset. Let X be in the span S, then X equals A10, 0, 0 plus B01, 10 plus D00, 0, 0, 0, 1, which equals A, B, B, D, as B equals B, because that we're just verifying that it's in our set W, which we defined above. As B equals B, X is in W. Thus, W equals the span of S as was asked. In this question, we have two subspaces, W1 and W2 of V, whose intersection is just the zero set. Now, here when we have two subsets, we would like disjoint, but all subsets contain the zero vector. So we actually call these mutually exclusive. And mutually exclusive sets, subspaces, are super important. However, what we're just caring about the fact that their intersection is zero. And what we want to do is we want to prove that if S1 and S2 are linearly independent, then S1 union S2 is linearly independent. Meaning here, if I have that these two are both linearly dependent, then this set's linearly independent, or the union of them is linearly independent, as long as the intersection is zero. Now, to prove this, I'm actually going to prove the contrapositive. And the reason why I'm going to prove the contrapositive is if we prove it directly, it's actually going to break up into a bunch of cases and gets ugly quickly. And you can try proving directly, which I encourage you to give it a try, but it blows up very quickly. And when that happens, think contrapositive. And the contrapositive here is if S1 union S2 is linearly dependent, then either S1 is linearly dependent or S2 is linearly dependent. You could also do a proof by contradiction where you assume they're both independent, assume S1 union S2 is linearly dependent, and see what happens. And you'll see that the proof by contradiction and the proving the contrapositive are pretty much the same. But here, suppose S1 union S2 is linearly dependent. Then there exists A1 through AN, B1 through BK in F, and V1 through Vn in S1, and VW1 through Wn in S2, such that A1 V1 plus AN Vn plus Bn W1 plus BK WK equals 0. Okay. Now here, we're going to say that these are not in S2. And here we're going to say they're in S2 and they could be in S1, meaning one of them could be the zero vector. So we're going to allow one of them to be the zero vector, but that would be one of these. And this means that no VI equals WJ. That's an important idea here. No VI equals WJ. But this implies that A1V1 plus ANVN equals minus B1W1 minus BKWK, which now this implies that A1V1 plus ANVN is in W1 and minus B1W1 minus BKWK is in W2. As they are equal, they are equal, A1V1 plus ANVN is in W2 and minus B1W1 minus minus BKWK is in W1 as W1 union intersect W2 equals the set containing 0. A1V1 plus ANVN equals 0, and minus B1W1 minus BKWK equals 0. As one of these constants is non-zero, or sorry, as at least one of these constants is non-zero, either S1 is linearly dependent or S2 is linearly dependent. And we've proven the contrapositive. And because we've proven the contrapositive, we've proven the original statement.